everyone. I'm Tamar Glaser. I'm a computer vision researcher and an algorithm developer at Alibaba-MIIL, which is Shin Intelligence Israel Lab. We're part of the DAMO Academy, which is Alibaba's international research division spread in several sites around the world. What I want to talk to you about today is a specific feature and model in our application, in our product, which is a photo application. And I want to relate to this model from two aspects, both from the product aspect and from the research aspect. And hopefully we'll be able to connect all considerations together, both the production ones and the research one. And we'll be able to show that it does relate to each other. A bit about myself. This is my career path. In the context of this course, was a Women in AI course about deep learning, I want to relate to the issue of being the only woman in the room. Well, I never thought it was an issue, as from the beginning, I was the only girl in the room. In an accelerated math program, I was the only girl who graduated. Then in my first degree, which was a double degree in electrical engineering and physics from the Technion, I was the only girl who graduated the Psagot Excellency Program of IDF. And then the next stage was in Rafael Computer Vision Department. Things got a bit better there, more women. The next stage was my master degree in electrical engineering from the Technion and the supervision of Professor Lihi Tzelnik Manor, which was actually my first major woman role model. I think it's related because when we see more women, in a minute I'll relate to it. The next phase was Albert Computer Vision algorithm department, and today at Alibaba. So refer to the only woman in the room issue. I didn't think it was an issue. I think it was just a fact, and that's it. And I didn't relate to it at all. But when you think about it with the years and with the proportion, I think that our subconscious feels more comfortable when similar people are around us. So I think that many women are not even aware to the fact that I wasn't, to the fact that we feel maybe a bit less comfortable to ask questions. We feel maybe more need to prove ourselves all of the time. So having more women around and having women role models, I guess it's something we should all strive for. Another issue about myself that I have to mention, of course, is my family. And in the context of women in AI, yes, I have 10 years old and 8 years old twins, and you can be a developer and a mom. You just have to tune a balance at the point you feel comfortable with. So I recommend. What I'm going to talk to you about today. So as I said before, I want to relate to a specific model, both from the research and from the production side. And the model would be part of a feature in a photo application. So we have a photo application. I'll present it. I'll present the feature. It is called the memories feature. It is composed of two main models. One is the event detection, and the other one is the event recognition model. We'll just briefly mention the first one and then deep dive into the second one. And this would relate to the paper we've just published regarding photo event recognition. And we'll see, hopefully, the research and the production merge together. So our photo application is similar to photo application that you all know from your cell phones. Photo applications are meant to manage a huge amount of photos we all have on our mobiles, and it should take care both of backup and privacy and stuff like that. But in the aspects of computer vision, it should take care of automatic management of our photos. And when I say automatic management, I mean things like enabling search and enabling automatic friends and family images gathering and clutter removal and generating automatically albums. And these are the things that we want to have as cool features in our photo applications. So what's behind the scenes for these cool features? We have many computer vision models behind the scenes for this photo application. Models that some of you may know really well, such as image classification and face detection, and also content analysis and quality analysis and image similarity and image selection, and also, of course, and content creation. You can see here a small example of the crop suggestion, which is an algorithm that just have to automatically select the relevant crop out of an image according to its content, and content creation, and event detection and event recognition, which are parts of the model we'll discuss in a few minutes. So when we come to design a new feature or a new model, we have to know the system. We have to know which models already exist in the system. And we also have to know the product consideration, the engineering consideration. We have to be aware of efficiency constraints and parameters constraints. And where do we approach? Do our model have access to the images themselves, or it has to use only pre-computed attributes and metadata? So we have to be aware of all of this stuff. So now we're gonna look at the memories feature and see if we have all other models and we don't have these two models, how do we design them? What is the way of thinking? That's what I want to that is what I want to talk to you about in the first part of the productization. So what are memories? Memories are collections of nicely displayed images that are related by something, and by something could be by someone, like images of a certain person, something like all images of the beach nicely displayed, by some time, like all images from October 19 nicely displayed and summarized, or by some time, but the time is not predefined but data driven. What do I mean by data driven? I mean that the user have a gallery of many images, and we can identify when something interesting has happened. This is an event, okay? We want to detect where an event has happened and then recognize its content. And these are the photos of the event memory. We would like to gather these ones and present a nice story about the events that the user had. So it's different because in a predefined time memory, we can query the database, and here we cannot query the database. We don't know where the event has happened. So we will relate generally to event memories and data-driven memories. And after we have the images, it's not enough. It's the input to the memories model. We'll have to do some image selection, select the relevant images that would tell the story in a nice way. And we should nicely display it and select a name and a cover and fit some music. So we can generate something which is nice. This has music on, and this is a memory of someone, okay? And our goal is to make the user smile. So if we can make it appealing, our goal is achieved. As we saw, the event memory is composed of event detection model and event recognition model. I said earlier that we have to know where we're standing. If we have access to the images themselves, or if we have access to the pre-computed attributes and metadata only, and all what is surrounding us. So briefly about the event detection, because it's the input to the event recognition model. Event detection scans a long gallery full of photos, and it should detect which images are where there is an event, okay? An event of important thing that happened to the user, and it captured it, okay? So this is event detection, and the challenges are to identify the interesting events in a gallery using, when we have the timestamps only, but when we have location information, we want to use that as well. But we can't limit it to the times that we have the GPS information, because it's not always on. We should be able to deal also with partial location information or not at all. And we want to use it when it is there. And we want to identify both events and casual images. A user gallery is not composed out of events only, of course. A user can have an event and capture several images, and then a few hours later, it could be at a store and capture a product and send it to someone. I mean, clutter images that does not interest anyone. And a few hours later, it could take a photo of his child, and is interesting, but it's not part of any event. So we all have both events and casual images, and we want to identify both events and casual images. In addition to identifying both events and casual images, you have to deal with different scales, because different people capture a different scale. There are some capture more, capture less. Scale is in both time and location, and the same person can even change the frequency of capturing in different times. So we have to deal with this and be robust to different scale, and we have to deal with burst shots. Burst shots is an issue. People never capture a single image today. They always capture a few images. Clutter, we have a lot of clutter on our phones, all of us, I guess, and screenshots and non-interesting content. We have to deal with all of it. And in addition, we have to remember where we stand. This is a wide scanning feature, a wide scanning model. It takes a lot of images in one time because it has to generate some statistics. Therefore, it cannot access the images themselves. It cannot see the pixels. It has to use only metadata and pre-computed attributes. So whatever there is in the database that is stored in advance. So we have to remember this one, and we have to consider it. Once we have our events detected, what we want to reach to is to analyze their content. Okay, this is event recognition. Generally, event recognition, according to what we said now, we have an event. We found a collection of images that are related because they're generating a specific event in the user's gallery. And now we want to analyze it. We want to analyze, is it interesting? Is it important? We want to analyze what's happening there. What's the type? To give a name to the event, to select the relevant cover, to select the suitable music, to select the relevant images, because we summarize the images. We do not use all of them in order to generate a nice memory. Okay, so we have to analyze all of this, but in order to formalize the problem, give it a frame, let's just focus on one thing. Let's say we have a collection of images and we just want to classify the event type. Okay, so if we just want to classify the event type, later on, once we have the event type, we can analyze further things like, is it interesting? Select the relevant images, the name, the cover. But first, let's try to understand what's the event type. So this is something that is previously researched in the academy, in the research, in the literature. And we have prior work. And one of the databases, actually, the largest and the most recent one is MLQFI database. And what I'm presenting here is images and data from MLQFI database. The citation is below. And we can just illustrate which kind of events we have there. Okay, we have their regular personal events such as wedding, birthday, graduation, theme park, beach trip, urban trip, cruise trip, Christmas, Halloween, show, zoo, casual family gathering, sports, art activity, casual things that we all do and we all have in our phone. So I think this is a generally representative division to event classes that we can all identify with. And this is a good framework to put our problem piece. So now we're starting to connect the product with the literature, but not yet. We're first analyzing what's the framework that we're in system-wise. Okay, so we have the existing models and we want to add now event recognition, but we do have to remember which models do we have and where do we live. So if we're approaching the task of classifying a photo collection, we can try to formalize the main challenges, the main algorithmic challenges. I see three main algorithmic challenges for event recognition. The first one is we're classifying an image collection. It's not a single image, it's a collection of a variable length with variable time gaps. The length of the series is unknown and the length of the time gaps is unknown and not fixed as opposed to video. One can capture a few images of an event, then wait a few hours, then capture another few images. We don't know the gaps. So this is one challenge. Another challenge is the fact that almost every event would have many irrelevant images. We can see an example here. The top 4 images of a wedding event are clearly wedding images, but middle ones are less clear wedding images. They might be, they might not be as well. But if we look at the bottom 3 images, no relation to event to the event wedding. So almost in every event, we'll see some partially relevant or irrelevant photos. And this is another challenge we have to cope with. And the third challenge I'm going to refer to is the image representation challenge. We have to represent an image in a semantic way, both the high level and the low level. Both the objects are important, both the scene is important. We have to include it all. And in addition to the fact that we have to represent the image in an inclusive way, we don't have such big data sets to train the representation. And image classification and object classification were used to 9 million and 14 million images. Here, the largest data set has less than 100,000 images, including training and test set. Okay, so we don't have these big data sets in order to train good representation. So it poses another challenge. In addition to the algorithmic challenges, we also have the engineering constraint, efficiency, computation, parameters, regular things that we have to deal with and consider. We do know that, as I said before, we live in our system. We know what we do have. We have image classification as an existing model. We can use it. We can use it to address the image representation challenge because it was trained on a large data set. So maybe we can do something with it. Maybe we can take the image classification model that we have. And in this part, I'm addressing, I think, the more basic deep learning level. Okay, in the next phases, I'll be addressing the more advanced deep learning level. But for now, I want to share with you the thinking that I'm doing in order to reach the conclusion that I've reached. If we have simple image classification, CNN, and we want to try to use it in order to do event recognition per image. So we'll take the existing algorithm and the existing network and the embedding, and we know that we have a fully connected layer that predicts that we have there the object's person key stress. And maybe if we add another fully connected layer that is trained to the 23 events of MLQFit, we might get wedding event for the first image and wedding event for another image. But what about the less clear images? We're probably we might get wedding there, but we might also get something else. And for the less clear images, the irrelevant images, we might not get anything, and we definitely won't get wedding event for this one. Okay, so if we use this approach, we'll get some non-random accuracy, but it's not good enough. So what we can do, we can aggregate the images, of course. We can use all of the events images. How? For instance, we can try to think of some smart way, not averaging, but taking the more relevant images with the larger weight with relation to the lower relevant images. Okay, so we can take something like confidence weighted summing, confidence weighted averaging. Okay, and in this case, the confidence of weighting for the relevant images would be higher than the irrelevant images, and we might get a better result. Okay, this is nice. Okay, we do get a larger accuracy in this way, but it's not enough, of course, because when we think about the product, we can't let ourselves that out of that in many cases we'll get wedding when it's not wedding. Okay, from the user aspect, it's just not good enough. Okay, so actually, what we've learned in deep learning is that once we have the option to handcraft a heuristic solution, it's not good. We should learn it. We shouldn't handcraft a solution. We shouldn't select some heuristics. We just should learn it. So generally, what we want to do is we want to aggregate the images, but we want to aggregate the images in a learnable manner. We want to tell the network, this is wedding, this is your ground truth. Learn that are required aggregation layers so that we'll understand that this is a wedding event. Okay, this is what we learned in deep learning. So we also learned that we don't want to give the network processed information. We want to give the network the raw information as we can. So we'll skip the fully connected layer and we'll give the aggregation layers the image representation. Great. Okay, but what is the architecture? The architecture of the aggregation layer should be stated. So let's think, what can we do? We want to emphasize the more relevant images and we want to lower the weights of the less relevant images. So this is attention. We want to draw the attention to the more relevant images. From this, we know the requested architecture. It's very natural to see that now transformers would be a good choice. So transformers everywhere. It begins from text and NLP, came transformers, and today there are also widget transformers, which compose of widget, vision, and temporal transformers. And naturally, sequence transformers could work as well. It does not exist yet, but it could work. So when we use transformers and we train transformers to detect the right event, we jump up the accuracy significantly. So this is our architecture. So far, I wanted to connect you to our way of thinking, but now I want to present the full architecture, and it also connects to the research part of the paper we've just published. So this is our architecture. We have, as I said before, NA samples, NA images, the length variable. We don't know what NA is, and transformers does require a fixed number of images. So we sample a fixed number SA images out of the album. Okay, so this is the first part. For now, we want to say that we just random sample. Later I'll explain more, but for now it's a random sample. And next, for each of the images that we've just sampled, the SA images, we run our feature encoder, our image classification, and we have SA images. Each of them is encoded to D dimensions. This is our image classification encoder we used, as I explained before, and we have our first album representation, which is SA times D. Okay. Now the next stage, we add a positional encoder. Generally, a positional encoder is added to a transformer a representation in order to have the relations between the tokens and to cover both global and local relations between the encoder, and to let the attention mechanism to know the distances between the different tokens. In our case, this is not the use of the positional encoder. We use a learnable position encoder in the same manner that is used in temporal sequences. But here, what we have is we have a positional encoder that is used for another usage. It's more for augmentation. We'll see it next. The next phase, now that we have our album representation, which is SA times D components, we add a classification token. The classification token is concatenated at the beginning of the album presentation as an additional token, and it's aggregating information of which images are more and less relevant for the task of classification. Okay, it learns, it's a learnable item that learns how to gain more weights for the more relevant images and less weight for the less relevant images. This is our album representation. That is the input for the transformer encoder. The next stage, we have generally L layers, in our case 6 L layers of transformer encoder. Okay, this is the input for our transformer encoder. We'll dive into these details in a few moments. And after an MLP layer to classify, we get the event class, okay, and another output, which I'll explain shortly. So moving to the research part, okay, moving to the research part is the same, it's the same model, no change, the same architecture, but I want to analyze it from the research aspect. So we've just published a paper. It's called PETA. You can search for it. It's photo album event recognition using transformers attention. And if we analyze these 3 algorithmic challenges that we've just analyzed before, we want to relate to how previous works dealt with these challenges. So for the fact that we want to classify a photo collection, previous works tried averaging and weighted averaging and just in recurrent networks and LSTMs and GRUs. And generally what I can see is that As we've said before, an album is not necessarily an ordered set of images, and local relations are not more important than global relations. And LSTMs, although it is meant to catch a little more than the local relations, it's local. It's still local. It still have some limitations on the temporal time window, since the propagation of the information is not as far as the whole sequence. So transformers helps us with this information. In addition, we have the attention mechanism, which helps us with irrelevant or partially relevant images, as we saw here, and the high-level image representation that we need, the semantic image representation as a small data set. So previous work tried to solve it using ensemble of networks, such as ensemble of pre-trained networks on object data and a pre-trained network on a scene data set, and trying to do coarse to fine representation and all sorts of stuff. And we solve it using the proper image classification model with the proper pre-trained data set. And we'll reach to this as well. So back to our architecture in relation to the main challenges going through. So the photo collection, the set of images is addressed through the sampling that we've showed here. So the sampling is not exactly random sampling, it's random permutation sampling. And why? Why? Because we said that an album is not necessarily ordered. No one said that in order to classify correctly, we have to know that the beginning of the event is at the beginning and the end is at the end. Trips are not ordered. Trips, for instance, it's not related what's the order of the images. And the variable time gaps also makes the set not necessarily ordered. So the order is less important here generally, and we can do random permutation. And why does it help us? Since data sets are small, as I said before, when we do random permutations, we do, in fact, album augmentations. We enlarge the number of albums we have for training. So the random permutations help us with augmentations, okay? Then the image representation challenge, we already saw how we deal with that. We use pre-trained data set, which is open images v6, and we'll see why. And the next challenge of the irrelevant images is addressed through the transformers. We have another output there. I've ignored from it previously. This is the image importance. What is the image importance? We saw that the transformers enable us to learn which images are more relevant and which images are less relevant. Where apparently previous works also wanted to explore these things and wanted to understand which images are more and less relevant, because it affects dramatically on the event recognition results. So we have annotated data set of image importance. MLQFIT dataset was previously started from QFIT dataset before multi-label. The citations are here below. And there's an annotation of a score called image importance, which indicates how relevant and how important each image is within the album in order to detect the album class. So annotations got the task to annotate these images and to score them and to rank them and to tell which images are more and less relevant for the album without really detailed instructions, because this task is highly subjective. And you can see here an example just to demonstrate what's image important is. So this is from their paper, from MLQFIT paper, okay? It's an album. It's the five images out of an album that was classified to zoo mistakenly, but then was classified correctly to theme park. And we can see why. Because if we focus on images such as the chicken image here, we can mistakenly predict it as a zoo event. But if we focus on a more relevant images with a higher score, we can correctly predict it's a theme park event, okay? So the previous work did designated ranking loss functions in order to predict the image importance using the original annotated image importance ground truths, okay? So the training here was using the annotated ground truths. There were iterative processes such as learning the event recognition, then learning the image importance, and repetitively, iteratively converging. And even in 2020, there was a work of expanding, automatically expanding the image important ground truths to include more. Okay, and all of these works used the image importance ground truth annotation to train the image importance prediction. It is a subjective task. Not only that it's hard to predict it, it's also hard to annotate it. When QFIT paper checked the human annotators correlation, Spearman correlation between the human annotators, they found that the mean Spearman correlation is 0.4 on average, meaning there is a correlation, okay? They agree with each other. We can see why when we see images, but the correlation is not as high because the task is really, really subjective. So what we aim to do is we aim to extract, in addition to the event type, the image importance. The image importance here is image importance per image, but we do not train for the ground truth of image importance. Okay, so once we've understood the input and the output fully, let's formalize the problem. We have the input. The input is a photo album with NA images, IT. We have two types of output. One is the predicted event type, and the other is image importance. The predicted event type is actually not a single class, but it's a multi-label data set. Therefore, we're extracting the confidence score for each of the classes. And the image importance is predicted per image. Okay. So the first stage we said we do sampling, random permutation sampling, batch size should be a multiplication of the sample size. Then we do image representation for each of the sampled images. Then we start with the transformers phase. When we start, we take the first embeddings and add positional encoding, which is learnable. This is used, as we said before, since it's random permutations, position doesn't really matter, but it helps us as a album augmentation technique. Okay, and then we add a class token, concatenated at the beginning of all images tokens. So now we have the input for our transformer encoder. It's the tokens of the images concatenated with the class token, and we enter the transformer encoder. So we have L stack transformer encoders here, and this is our tokens. And let's dive into the transformer encoder. The first stage after normalization is a multi-head attention. We have here a great image that simplifies it. The credit is here. The first stage is taking our tokens and projecting them with linear projections to value, Q, query, and key. We have age heads. It's a multi-head attention to allow attention mechanism to realize both global and local relations. So we do the projection into query, key, and value. Next stage, we do the scale dot product attention. The scale dot product attention is actually multiplying query and the key, scaling it by the age, and then doing softmax over the whole matrix. The softmax actually would pop up the more relevant images and will lower down the less relevant images. This is the attention mechanism. This is the heart of the attention mechanism. So we have now the output of the multi-head attention. This is these Zs. They're having, we have a norm and an MLP layer and a residual connection, and we're up to our next transformer encoder stacked on top of each other. Okay, so this is the output of the transformer encoder part. And in order to predict the image importance, we take the last encoder from the transformer encoder layers. And this is a SA plus 1 times SA plus 1 dimensions. We have age attention matrices, and we average them all over all heads. And now we have a single attention matrix at the output of the last encoder layer. Okay, this attention matrix is actually composed when the first layer of the attention matrix derives from the classification token. Okay, because we concatenated it at the beginning of the tokens. So if we take the first layer of the classification token, we have the image importance prediction. As simple as that. We learned it implicitly without telling the network we want to predict image importance, but we do have significant information. So to our results, let's look at some input examples. This is all images are from ML QFIT data set. Citations are here. a really easy example of a holidays data set, of a Halloween data set, because a Halloween event, because all images are relevant. You can see here images that are irrelevant. When we go to this wedding event, we already see some images that are less relevant. For instance, these images or these images, some of these images are, we can see that it is a wedding, especially not close-ups. This is a group activity. It's maybe a little harder event to realize because we have to connect all in order to realize what's happening here. This is a multi-label event. The ground truth has both bit trip and orbit trip. The prediction detected both bit trip and trip. Okay, so here we can see that it is a bit trip and an orbit trip, and we correctly detected both. Casual family gathering. This one is, again, subjective, because this one is clear. We see many people gathering together, eating. It's a casual family gathering. But this one is also a casual family gathering that was correctly detected. Okay, how? We see here that this is a casual family gathering, but since the length of album is unknown and the gaps are unknown, we can see here many images captured within a few seconds. So some events could be really hard on the aspect of irrelevant images. I guess this is a good example of how can some event be really hard on the aspect of irrelevant images. So some quantitative results. We have, generally, there are 3 publicly available photo albums event recognition data sets, and we examined our architecture on all of them. Okay, there are some additional data sets of event recognition for single photos, but it's not our task. Our task is for albums. So the 3 data sets are MLQFeed, PEC, and holidays. We run our algorithm on all of them, and we get the superior results on all of them. We can see here that specifically MLQFeed, the reported results, the best reported result without image annotation, image importance annotation was less than 83. With image importance training, it was 84.5, but we got without the image importance annotation over 90% map. Okay, for PEC, we report both map and accuracy, because some of the previous work report accuracy and some report map, and so to compare, we computed the both and we outperformed on both aspects. And holidays is not recent data set, so recent result on it are irrelevant. It's really low, so we reported only the CN aggregation baseline here, and we can see here that it's saturated according to our algorithm as well. So this is generally our quantitative results, some qualitative results in order to illustrate the attention mechanism. So we can see here Halloween event, okay, and on the left you can see here the top 8 ranked images according to the image importance prediction. This event, if we take the baseline of CNN aggregation, it was mistakenly predicted as a birthday event, and we can see why. Okay, if we look at these images, we can also think that it could be a birthday event. But if we rank the images correctly and we refer more to these images with the high image importance prediction, we can correctly detect that this is a Halloween event, and our algorithm correctly detected that this is a Halloween event according to the ground truth, but also according to our detection. So this illustrates the importance. So the left top 8. The left are the top 8 according to the image importance prediction, and the right is the bottom 8 according to the image importance prediction. These are great photos, but they do not help us with class prediction. Regarding the image importance prediction quantitative results, so the upper bound is the ground truth correlation, the ground truth annotative correlations. In QFeed original papers, they took the annotators and they do a 2-split among all annotators, and they measured the Spearman correlation and reached to 0.4. With confidence ranking, when we take the top confidence of per image classification, we get 0.3 with comparison to the ground truth. Okay, comparing the confidence to the ground truth by ranking, by Spearman correlation, we get mean Spearman of 0.3. And with our image importance prediction, we get 0.374, but without the usage of the ground truth. Okay, we compare our prediction, our implicitly learned prediction, to the ground truth, and we get 0.374 for the mean Spearman correlation. And we can see here a qualitative example that shows from a religious activity event, we can see here that the top 5 ranked according to our prediction are relevant, and the bottom 5 are less relevant, while when using the per image confidence ranking, the top 5 are not necessarily relevant, and the bottom 5 have both relevant and irrelevant images. So this is regarding the image importance prediction. We did some further ablation studies, such as looking in order to, we have several parts in our architecture. So we did some ablation studies to examine different aspects of the architecture. One of them is referring to the number of sampled frames, number of sampled images. So we used 32 images, but also we examined 16, 8, and 4 images. We compared the map over the different number of sampled images, and we compared the training time, the inference time. The inference time here includes also the CNN extraction of the image representation. If I return to the product and the system, we already have it in the system, so we can save this time by good engineering. So, and the transformers part could be much less. But this is the overall time of the system. And we can see here that even with 16 images, if we have some other constraints, we gain great performance. And even with 8 images, only 8 images out of an album, we outperform the current state of the art. And this is thanks to the strength of the attention mechanism that knows how to draw the attention to the more relevant frame and more relevant images. So taking only as few as 8 images helps us to correctly predict most events. We further did comparison regarding the backbone. So we used TWESNet backbone, which is a backbone developed in Alibaba, but it has open source in GitHub, so everyone can use it. And we showed that it outperforms. We also did some ablation regarding the freezing of the backbone, because we said earlier that on the product side, we want to reuse the backbone that is already there for image classification. Okay, and since we have small data sets, unfreezing the backbone doesn't necessarily help us. So both from the product side and from the algorithmic and research side, we should keep the backbone frozen. Pre-trained data set, I mentioned earlier, there were previous work that tried to merge several pre-trained data set networks using an ensemble. We used OpenImages v6, which includes both high-level and low-level classes. We can also use just ImageNet, but ImageNet 21K is better. We examined the loss function, and we examined the sampling. As I said before, using the random permutation and the positional encoder, we get, in fact, some album augmentation for our training due to the fact that we have small data sets. So this is it. All details are also in the paper. Generally, my message is that behind the cool photo application, we saw many complex computer vision models, but we have to consider what's in there and what's not there, and what's our constraint product-wise and engineering-wise and efficiently-wise to get the best solution for this specific system. And once we examine it, we still can get the state-of-the-art result research-wise. It doesn't contradict each other, and we can gain both of them at the same time. We saw event recognition, we saw some of event detection, we saw event recognition as a new transformer application usage, and we saw the image importance that we could learn it implicitly without the specific task annotation and without using the specific ground truths. Eventually, we want to have a nicely displayed memory that would make the user smile. So that's all. Thank you very much.